Good afternoon and welcome to Intro to Dispersion and Milling. My name is John Kowalski. I'm part of the marketing team here at Vic Gardner and would just like to welcome you. We are recording this presentation and immediately following you'll receive an email with a link to the recording that you can view later or share with colleagues. Also, time permitting, we may have some time for questions and answers. So if you have any questions during the presentation, please log them in the chat function. It should be in the bottom right-hand corner of your screen, and we'll get to them time permitting. If we do run out of time with the presentation, Andy, our presenter, will, or someone from our field team will be getting in touch with you directly. So with that, let me turn things over to Andy. Andy Stummer is our business line manager for Dispersion, and around the office, we call him the King of Dispersion. So with that, there you go, Andy. It's all yours, sir.
Thank you very much, John. Thanks, everybody, for coming online today. We're going to talk about the introduction of dispersing and milling. It's kind of an entry session, and to have better connection, we'll turn off my camera and make my screen a little bigger. So I can talk. Okay. All right. Okay, so we're just going to go through a couple of slides, giving you guys an introduction on who is VMA and BIC and the relationship. Then we're going to dive right into some of the basic principles about dispersion. And we're also going to cover different types of equipment for lab as well as production. And then at the end, we're going to talk about the QC process, what kind of capabilities we have, and also our laboratory overview in Germany as well as in Wallingford, our sister company, BIC Additives, where we opened a really nice lab about 2 years ago. And unfortunately, last year, everybody knows with COVID, we weren't really able to go into the lab and do a lot of trials. But I have good news. It's been reopened. And anybody interested in doing trials or review the technology, we'll welcome everybody back. Okay. So VMA Getzmann is the manufacturer of this nice equipment. They are known to make really high quality laboratory pilot and manufacturing milling and dispersing equipment. The company was founded in 1972, so this beautiful couple on the top right, they're still around. Herman actually still comes into the office once a week to ensure that they still follow his design philosophy, and we'll talk a little bit about that later. BIC has had the exclusive distribution rights since 1988 for North America, US, and Canada. It's still owned by the same family. The business is now run by the two sons, Christian and Martin. They have about 100 employees and they're growing pretty fast. And they are known again as a high-end manufacturer of dissolvers, bead mills, basket mills for lab, as well as your pilot or manufacturing requirements. So here is a slide showing kind of the facility layout. The company is located about 45 minutes east of Cologne, Germany. Everything is designed in-house and also built in-house. So that building right here is a brand new building that they just added on last year. And they have a new design center in there, as well as new office space. And it's a pretty forward-thinking company. One of the great things about VMA was that about 40% of everything that they make is custom. So we can really go and meet all the customers' needs for different dispersing or milling requirements. And they cover the entire line from lab, very small, all the way pilot and all the way up to production. About 2 years ago, we actually started to introduce production systems here in the US and Canada, and it's doing really well. And then we have, as I mentioned earlier, a really nice lab up in Wallingford where we can, look at the technology and trial customers' products. But we also can leverage the synergies that we have with our colleagues at BIC Additives and tie them in if there is questions about formulations or you want to improve, your products. So we can help you there. Just give you that additional support that no other company has the capability really. So we're not just a hardware company, but we also bring the other components to the table. Basically, the products, the Dispermet line is for many different applications. So ideally, we use it to disperse different types of pigment classes. So we have the organic pigments, inorganic pigments, and then of course we have functional pigments, and then the metallics or the special effect pigments are also very popular. And the whole idea is really to improve the quality of our products by, have a better gloss, transparency, and color strength. Some of the most important attributes that we want to improve on, and that's the reason why we want to disperse our products. So obviously there are some important key elements that we're looking for. So we want to improve our wetting. These van der Waals forces, these magnetic forces, the binding forces that keep our pigments clustered together, these agglomerates or aggregates, we really want to break them up. And the idea is to eventually get down to the primary particle size. Some of them go down in the nano range. We can easily do that as well. And that will lead us to just a better product. Again, with color and gloss and the overall appearance are some of the elements that we're really improving by using the proper equipment. Also, the pigment efficiency. If I disperse properly, I don't need to use as much pigment, so there's a cost angle there as well. That's really important. And then obviously we're going to have improved product consistency. Our formulations will improve, and we also have a more consistent particle size distribution, and that will also lead us to better upscale results also when we use the right technology, and we have different software packages that are geared towards having really good upscale results from lab to pilot and manufacturing. And we'll cover that a little bit later. So some of the issues that come up, and we get a lot of calls, is like customers, they have issues with color change or poor stability, flocculation of pigments, sagging, leveling, settling, or gloss isn't there, or we have haze. That's another one that's not on the slide there, or separation. So this is all these areas we really want to improve by having a better dispersion. So stability, obviously. So pigments require really strong color fastness to reduce the fading over time. Also, the brighter the product, the better usually our color. And then obviously pigment size is very, very critical. We want to reduce it as much as we can because that will just give us a better appearing product, not just color, transparency, gloss. And also, again, it helps us save money by having a better dispersed product. We're able to just use less of it, and that shows up in the bottom line. And then obviously viscosity. So if our viscosity is lower, not too low, we can put enough energy, but in a good range between 1,000, let's say, to 10,000 centipoise. Ideally, we should be having a really good sweet spot for optimization of the process and getting really good particle size distribution on the processing. Okay, so it's very important to remember we don't want to destroy, when we're dispersing, we really don't want to destroy the pigments. We're really only looking for reducing the particle size. And basically we have these larger clusters of particles. These are called agglomerates. And then we want to reduce those with shear forces to turn them into aggregates. So we would use a Cowles blade for that. And then ideally, the second important step to go from the aggregates down to the primary particle size, we need to do medium milling. And really the shear forces are what's responsible to get us down in particle size. So when we accomplish our goal at the end, then we would also need to keep our particles in a suspended state. And for that, we can use some different additives that help us achieve that goal. And obviously, a lot of you people are familiar with big additives. They have a really good range of different products that go into the formulations. So here's just a quick slide showing you just the different particles or pigment particles, and ideally we want to just break up these agglomerates and aggregates. So here is a good slide just showing you and outlining like the agglomerates here. These are the larger clusters of pigment particles bound together by these van der Waals forces. And if we want to go from the agglomerates down to the aggregate level, we really need to use a cow's blade, ideally, to get these clusters reduced to the aggregate level. But if we want to go from the aggregate level down to the primary particle, the cow's blade is no longer efficient enough, because we can put in the shear needed to really break up these binding forces at the aggregate level. We need to use media. So that's why we have also milling equipment we're going to cover that helps us to go from the aggregate level down to the primary particle size. And obviously, these particles then need to be stabilized, and that's where the additives come into play. So here's just a nice slide. I really like it. So we have first the cow's blade, which we call that the predispersion process. We're wetting and then breaking up these agglomerates. And then when we get to the right size, usually the threshold there is between 20 to 30 microns of particle size. Anything smaller, then we want to start the grinding process with the media milling. And therefore, you can see a picture of the rotor right up here, or the milling tool that allows us to do that. Okay. Here is a great slide that just shows you the different technologies and the sweet spots for each of these technologies. So first, we use a dissolver. And then if we want to go really small to the primary particle size, we start using the bead mills, where they're really efficient. And there is 3 different technologies we're going to cover. I'll just explain or give an overview of how they function. Okay, so first we have the predispersion, which is basically the step 1 with the dissolver. And there we have a whole different range of different models that we offer with different capabilities, also different sizes, depending on how much product you want to do. And then the second part is the fine grinding or the media milling. You can see there is some numbers right below. So we have 18 to 25 meters per second. That's the ideal tip speed window that we're looking for to optimize the dispersion process. And then when we do the fine dispersing, the grinding, our rotor speed should be between 10 to 16 meters per second to optimize our dispersion or fine grinding process. So for that, on the milling side, we have obviously the vertical bead mills, which are basically a pop mill. We have a system they're called an APS we're going to cover, and then we have the basket mill option there that will help us do that, which is also referred to as an immersion mill. And then obviously there is the horizontal bead mills that a lot of you probably are familiar with, and we have some very good solutions there as well. Okay, so in the first part, obviously, which is our predispersion process, we always want to optimize our ratio of our dispersion plate to our container. Should be about 1/3. And I really like this table right here, and we can send you a link that kind of outlines each. This is more for the lab space, each container, and what is the optimum dissolver blade diameter that you should be using for each of these different container sizes. And that's really important. And why is that important? It is important because we want to optimize the dispersion process, and we would like to get a nice looking donut. And then we'll show you a couple slides there. The donut is actually the visual cue that allows us to see how well is my dispersion process working. And in order for you to calculate that optimum tip speed that will get you into that nice range where you will get to a donut, you can see the formula right there. So it's the RPMs multiplied by pi and the diameter of your milling tool. If you want to do meters per second, then you just divide the whole thing by 60, in metric, and that will get you to that 18 to 25 meters per second if you are optimizing the critical parameters like the RPMs and the right diameter milling disc. So here is the donut effect. It's actually a really nice picture. You can clearly see that in this case it's been optimized and the donut appears, and I would know when I see this, the process is working well, and I should get a really nice dispersion with this setup. Optimized, obviously, with the right tip speed and the right blade diameter. Obviously, some viscosities are a little bit more challenging, so you can still get a proper dispersion. Let's say your viscosity is very low, then it's probably more difficult for the donut to even form. So, you know, if you have a product that's similar to like a water in terms of viscosity, so very low, you probably never see a donut, but that doesn't mean that you don't get a proper dispersion. It's just that when we make paint products, paint dispersions, usually we talked about the sweet spot there in terms of viscosity. It's a normal, let's say if I have 3, 2, 5,000 centipoise, I should see a really, really nice donut forming when I optimize my parameters. So what happens there is basically I have my cow's blade, and then right here on the edges where I have these, you know, these sharp corners, that's where I'm actually shearing my product, my pigment, and that's where I break up these binding forces. And that, if everything is properly set up, I should be able then to see the nice donut. So here you see an example of a really nice looking donut. We have 21 meters per second. The energy input is about 850 watts. And so it appears that we're doing something right in this case. Now, fast forward. In this case, we see a splattering. We still have 21 meters per second, but we're not introducing the right amount of energy. Therefore, we're not actually getting to a proper donut. And now I'm not optimizing my dispersion window, and it's not going to lead to a very successful dispersion result. Or if it does, it will take you much longer to get there. In this case here, we're actually putting in too much energy, and basically the product is just getting thrown around the container. There's really no proper dispersion taking place as well. So in this case also, diminishing return, it would just take you longer to get the results if you get there. Of course, it always depends on the type of product, but usually it would take you just a lot longer to achieve the right particle size. Okay, so this is a good formula, just dispersion result related to a mechanical power. P is 2 times pi times the RPM and torque. So the difference is now obviously between the dissolver and the bead mill. So of course, if we want to go to primary particle size, again, we know now that we need both systems. We start out with the dissolver. So here we use a cow's blade. Obviously, because of the design and I'm not using media, I'm going to have limited energy input, translating into also limited shear force. And it's only the first step of my overall dispersion process, and only used to de-agglomerate my products to get down to the aggregate level. And so there is really no real breakdown down to the primary particle size. So anything less than 20 microns, that's the rule of thumb. In some cases, you go down to 10 microns, depending on the product, but most often at 20 is where you kind of need to move over to a bead mill or to milling to really break up these binding forces. It is imperative that you always pre-disperse first before you start milling. Otherwise, you're not going to get the desired results because of the kinetic energy of the beads may not be strong enough to really break up these binding forces of the larger particles. And you could also clog a screen, which we see happening a lot of times, or a dynamic gap if people just go straight to a media mill and not doing the pre-dispersion first. And then obviously, if you don't do milling, then you're going to have just some appearance attributes that are not going to be ideal in color attributes. So you really want to do proper dispersion first. And then we move over to the milling part, which allows us now obviously to add a lot more energy. We have the beads in there. We have rotors. There's a lot of movement. There's a lot of energy build up inside of our milling chambers or our basket. And we really now have the ability to go down to primary particle size, even down to nano, sub 500 nanometers is not a problem. And that will give us a really nice looking product and definitely much better quality. Okay. So we want to always optimize our dispersion results. So it's about how long am I dispersing, obviously. Usually the pre-dispersion process, rule of thumb, anywhere between 15 to 30 minutes. And then we should have the right particle size to allow us then to start milling. We want to look at that visual cue, what we talked about, that donut effect. Tip speed, again, really important. Optimization there between 18 to 25 meters per second. If you go faster, you're just, again, putting too much speed in there, and it may not properly disperse or take you longer. And if you don't put in enough speed, then obviously it's going to take you much longer. Geometric consideration, again, the blade diameter, the type of blade is also really important there. And then obviously, how much product do I have in my container? We usually recommend about 50% of the container fill rate. And then in some cases, you can go up to 70%. I wouldn't go much higher, where you're going to have some spilling of your material, which is not very nice. And then optimize your pigment and filler concentration. Try to keep the temperature as low as possible. Especially when we are milling, we're putting in a lot more energy, and their temperature control is really critical. And then obviously select the right additives to help you maintain the product quality. And then at that point, we can move over to a bead mill if we want to go really down to primary particle size. Okay. So on the bead mill, we have the ability to put the higher energy input. We already had that slide. I'm not sure why it's coming back. Sorry about that. Bead mill setup is really with the rotor, and I have my beads inside. And now you can see already the beads will collide or drift towards each other, and the shearing really takes place as these beads drift towards each other and away from each other in these corners. So impact and shear forces are responsible for breaking up these binding forces. So we're going to de-agglomerate, ideally go down to primary particle size, better wetting, stabilization. And then if we want to go nano, we can even go nano. We have nano kits with our technologies that allows you to get there. So kinetic energy is really the key word here. That's the force of the beads hitting your aggregates. And basically, the heavier the beads, the more kinetic energy we have. Imagine you have some, a walnut, or in this case, a nail. You take one blow with a big hammer and it cracks open, and I would have to do many, many blows with a small hammer to really crack it open, if it even cracks open. So kinetic energy is always critical in having very good dispersion results. So there is a slide here. I really like it. Just shows you a comparison between a glass bead and zirconium oxide serum stabilized. So you can already see the specific gravity is almost 2.5 times more on a zirconium than on a glass. So it's also much harder, the wicker hardness. So they will last a lot longer. The problem with glass is usually they always shard. Break up. You have shards in your mill base, and you got to filter them. They were very unevenly. So that will also give you inconsistent dispersion results. And we just don't recommend glass beads at all. So if you can stay away, always get higher quality beads. It's much better for your process, and you'll be happy you did. They also last a lot longer. So here is a slide just showing you the different, like the beads right here. And then what happens here is, as you see, these collide together, and the shearing, actually, the particle size reduction is actually happening right here in these corners. As these beads drift towards each other, hit each other, and away from each other, that's where I'm building up all my energy. And that's what's causing the breakup of these van der Waals forces is happening right in here. Okay, so here are some very important parameters we got to consider when we are milling. So obviously we want to have the smaller the particles after our predispersion, the better. Bead size, again, is very important. It's also because of our kinetic energy. So if I have larger core particles or aggregates, I want to use larger beads. Usually we start out with 1 millimeter to 1.2 millimeter, and then we work our way down depending on what is my primary target. If I want to go down to nano, like sub 100 nanometers, we also have 0.2 millimeter screen beads, and then a 0.1 millimeter screen, or we have other technologies like with dynamic gap on the horizontal mills that also allows us to go down into the nano range with just a little bit of a different setup. Then obviously the bead loading is very critical. And again, the quality of the beads, how are they worn, are they consistent? We always want to have proper shape. And we have seen some really inexpensive beads on the market, ceramic beads. The test samples looked great, but then when you start ordering them, they just didn't look good. They were oval in shape, and you want to avoid those. They usually are cheaper. You want to always maybe pay a little bit more, but you get a much better quality bead. Again, the speed of the milling tool, our rotor, is a little bit lower than when we predisperse. So here we're looking to be in the range between 10 to 16 meters per second is our sweet spot. A lot more energy build up in our milling process now than we will have in the predispersion steps. So the cooling there is really critical. We have proper cooling capabilities with our basket mills, as well as with our pop mill, the APS, and our horizontal mills. We'll cover that. Then obviously milling time. How long am I milling for? The longer usually, the better my results get, more even particle size distribution in smaller particles. And then obviously, how long is my mill base staying inside of my milling chamber? Or how often does it cycle through it? So all these are important variables that will influence my milling process and my end result. So, and then obviously the viscosity is really important there. If the product is way too thin, again, like viscosity, like water, and I'm running an immersion mill or a basket mill, I'm just not going to put in a whole lot of energy. So it's going to take me a long time to really be able to mill down my particles. So always a little bit more viscosity is better. But if my viscosity is too high, then I no longer have a flowing product. And especially in a basket mill setup, it's going to be critical that my product flows properly, because if it doesn't, it won't go through the basket. And also on horizontal mills, viscosity is really important there as well, because you want to have a proper flow through the milling chamber and that it comes back out if you're going to go in recirculation or pass through mode. Okay, and then again, the tip speed is 10 to 60 meters per second there. And then obviously the type of milling system that we have, are we using an immersion mill, the horizontal, or the APS system? Okay, so just one important note. Early on I mentioned the design philosophy of Mr. Getzman. Here's a great example of what we mean by that. So we have one dissolver, and with this dissolver, we can now retrofit any other part on there that we think we need to properly disperse our material. So we could add a rotor stator for homogenizing. We could add a vacuum system if people don't want any air entrapment. We have here the APS system, which is that vertical bead mill. It's like a pop mill. We have a wall scraper system as an attachment, or the TML basket mill or immersion mill. That's also an attachment. So we have what's called this quick change system, which is a really great design. And basically you see right on top here of my shaft is a clamping system. This whole thing is like a bayonet style change system. So I can open this clamping ring right here, turn this whole assembly 180 degrees, and then I'll just replace my shaft with my cowls blade, and I just put on any other attachment that I want right on here in less than 1 minute. So it's really easy to convert the system into anything that I want to use it for. That also means less laboratory space is wasted because you have one machine to do a lot of different applications, and that's a very nice way of going about it. Okay. So here we're going to dive into just the design of different milling systems. So we have here a classic basket mill. We call it the TML system, stands for tourist mill. Here is an attachment to a Dispersion, what I just showed you earlier. And then basically here is the design. So on top we have a pumping and steering wheel right here. That's patented, and that basically has a purpose of drawing your mill base inside of the basket right here, okay? And then right below we have our milling disc, and then we would feed the beads right in here. So this whole thing is filled with beads. And then on the bottom of my milling disc, I have a screen, and right below the screen, I have another cow's blade. The cow's blade right there is great because it does two things. It sucks the product through the mill and through the screen right on the bottom, and then it kind of pumps it back around to the top of my container, where then this vortex wheel right in here will then draw it back in. So I have a really nice flow and circulation of my mill base through my basket mill. And that's really important that I'm efficient there. These milling discs right here, depending on the application, they can either be just like a Teflon, or we also offer different ceramic types, silicon carbide or zirconium, depending on what you want to mill down. That's important because if color stability is also very critical in a lot of dispersion applications. And if I use just, standard steel components, or the wall is steel in here, then that will wear off over time, and that could discolor your product. We see that, for example, with a lot of white products, Tier 2 applications, where some customers use stainless steel, components, and all of a sudden they're surprised that the slurry turns gray. Okay, obviously you had discoloration through your mill, and therefore we recommend that in these instances, purchase the ceramic components to avoid these type of problems from happening. We have a very intricate cooling system with our mills. So we have a screen on the bottom. Some of the competitive basket mills, they have the screens on the side. We feel it's more important to cool that area because there is most of your energy is being built up in here. So we have actually cooling lines that go around the basket. And on our manufacturing grade, we also cool the top of our basket. So the entire basket is really cooled properly by that design. And that is very important because most of my energy that's being created takes place right in here. So if I'm using a basket mill, I recommend cooling your basket as well as use a double wall container to properly also cool down the mill base as it gets moved from in and out of the basket and circulates through it, to keep the proper temperature. Last thing you want to do is overheat the product and ruin it or create a safety hazard. For this system here, we also offer a nano kit, and that allows you then to mill down, I would say probably around the threshold there, 400 to 500 nanometers. If you're looking for smaller particles, then this system here is not recommended. Then we really need to look at the horizontal mills or the APS system, which is our pop mill design. We'll show you in a minute here to get down to these particles. So here is a great picture drawing, just showing you the basket filled here with the beads, and then basically the movement of the product through the basket. Okay, so the cow's blade right here, you can see how it just draws the product out of the milling chamber and kind of pushes it to the top, and then it gets sucked back in with that vortex wheel I showed you earlier. So it's a really good design. When I'm cleaning, that's also always the question is, how do we clean? Well, very simple. When I'm done, I just lift up my basket, I remove my product, I put another container right there with my cleaning solution, and then, depending is I'm doing solvent or water-borne products, so there's different cleaning products that people prefer, and then you just fill your container, again, about the same fill rate, 50%, and then I just turn on my dissolver again with my mill, and I just run it for a few minutes. And that does a really good job of cleaning my basket mill with the beads. If I want to do a super clean, I just have to open up my basket on the bottom and remove the beads, and then I can put them in a ultrasonic bath to improve my cleaning properties if you're looking for that. So here is an example of a production scale basket mill where we cool the entire basket, and then here on top you can see that screw right there. That's actually where we introduce our beads. You use a funnel, and then here you load your beads right here. On the smaller laboratory scale mills, we don't have that. We just add the media directly right into here. So what we do there is we just turn on the mill, the basket mill, run it at a very low RPM, and then we just feed the beads right in here. That works really well, and then we're good to go. And this here, actually, right back here is where we measure the temperature. That's also very important. We have a sensor that actually on the production scale is measuring our temperature inside of the basket where most of our energy takes place. And then here, obviously, we have cooling in, and then on that side, we have cooling out. So it's always nicely circulating through our double wall basket right there. Okay. So some of the features, it's obviously a batch system. So we can go up to about 2,500 liters in manufacturing. And then obviously very small, 0.05, a quarter liter with a basket mill in the laboratory setting. Very simple design, obviously easy to clean, or relatively easy compared to a horizontal mill. We have basically one piece of equipment with the dissolver and the basket mill that allows us to do both things, the predispersion and the fine grinding. Very easy to install and use. We recommend double-walled, obviously baskets. It is double-walled, but also the vessel with that. And then if you want to go down to super small particle size, we can use a nano kit that's available there. Okay. Here is just an example of larger mills that we have. Not the largest one, but that's what that system would look like. It's a TML. And very easy to scale up from lab to production. Our scale-up ratio is about 1:1. So that really speaks for the technology. It's really a well-designed system. We also have some customers who prefer to do this under vacuum. They don't want air entrapment, so we have the ability to disperse under a vacuum and remove any type of air products. Here is a great system. This is called we installed this in Missouri, 2 of them. That's the Dispermat TM production scale. And why the system is so great is because we have a 2-in-1 combination. We have this system is a dissolver where you do your predispersion. So you can see right back this gentleman here. There's a cow's blade. But when I'm completed with my predispersion process and I'm ready to do milling, I push a button right here on this control panel, and I can lower this basket right up here. And it comes right down, and now I have a functioning basket mill. So I turned my dissolver into a basket mill with the push of a button, which is really unique. It's a patented process. Nobody else offers it. And it's awesome because now the customer doesn't have to use 4 machines. He does everything on 1 machine, and he bought a second one because he liked it so much. So it's a really, really easy way of doing the entire predispersion and grinding all on one system. Really, really smart design. Then we have, mentioned earlier, the pot mill, or we call it the APS system. The APS system is basically a design where we have 2 containers. This is really only for the lab, not manufacturing. And we have in this top container, we have a screen on the bottom and we have a drain plug. We have our milling disc that's attached in lieu of the cow's blade. We just swap that out. And then when I'm done with my predispersion in the container, I just add my beads, and then I just swap out the milling disc or the cow's blade with the milling disc, and I have a lid right up here that comes with it. And you just push the lid down, and that becomes all basically enclosed. because you don't want the beads flying around. And then I can do my milling. When I'm finished with the milling, I can hook up an air hose. There's a socket on top. You can see that right here. And that allows me to purge my mill base through the container into the container below. All I have to do is remove the drain plug right here. And very easily, I can now drain my container and have a milled product in the container below. Beautiful system, very easy to handle, also really easy to clean, because all I have to do is when I'm cleaning, I put the drain plug back in place, fill this up with the cleaning solution, and run my mill for a few minutes. And then I drain it the same way as I drained my mill base. And now I have a clean container, clean beads, clean milling tool, and I can move on to another batch. This is a great system for somebody who wants to do a lot of milling in the lab, wants quick results, doesn't want a whole day's cleaning mills, and is not so interested in upscaling. Because this system doesn't really exist in the manufacturing environment, obviously due to the handling. So we have made some custom systems that are about 35 liters for some unique customer applications, but it's a stock item, it goes up to 7 liters. And the larger the APS system, obviously, then you need a really powerful motor and disper mat. So these large 7-liter ones require much larger disper mat than the small models for the smaller volumes, okay? Then here's an example of our lab dissolver. That's also, again, with that bayonet style flange up here, where I can swap out and put that APS on there, or the basket mill, or any of the other attachments. This is great because this is our brand new C technology right here. This is the flagship disper mat AE. And this model here is great because it allows you to store all the data, give each batch a different name. I can run this not only with a certain speed setting, but I can also have it with a certain amount of energy that I'm putting in. And then the speed will automatically adjust depending on the viscosity that I have in my container. And that's also very good for upscale. So it also shows in my tip speed, my torque, which is an indirect measurement of my viscosity, which is all displayed right here on this beautiful screen. And I have also really important, without this, these safety features I didn't cover, and they're very important. We have the container clamping system, basically, so the container is always clamped right in the middle. And there's a sensor back there that measures the pressure to ensure that the container doesn't wiggle around. So if it's not tight enough, it will show you on the screen, and then it wouldn't even power on unless you properly fasten the container. That's important because what you don't want to have happen is if you're running a solvent product, metal on metal, you don't want the blade touching the bottom of your container or the side of the container wall. That's not a good situation for obvious reasons. So that's really important. But the second safety feature, which is really nice, is what we call the working area. So I have the ability with the system to create or set a threshold on top and one on the bottom. And that allows me then to safely operate my disperser right in the middle of this range. So if you were to inadvertently lift up the dissolver while it's spinning, it would automatically power down once it crosses that threshold. So that also ensures that there is no moving blade outside of the container, and nobody gets hurt with a moving disc or product flying around your lab. So this is a really nice system called the AE with the C technology package, and it's also available in the explosion-proof design. So then, obviously, just quickly, and we're kind of short on time, but I can function my dissolvers as a homogenizer or as an emulsifier with the rotor stator, and then obviously just as a regular disperser or as a milling system with the right attachments. Okay. So quality control, just briefly. So again, this is the C technology. It's just a nicer, larger screen. So you can see it right here: speed, energy input, torque reading, timer function, temperature readout, and then obviously my critical tip speed we talked about. That's all displayed right here. And then I have the ability to store all the different batches, program cutout values. So it's a really nice system for the lab. And then obviously I have a simplified version also for production. That just gives you some of the core pieces of information. And then here I have the ability to program my own system if somebody prefers that, have your own control unit, especially for manufacturing. And then here, just a quick view on the software that's going to be updated. Actually, we call it WinDisp. So you can send all your data over to a computer. And then here you can watch the entire dispersion process in real time on a graphical interface and see each of these trend lines, your speed, your torque, your temperature, and just basically showing you where these variables are. And then basically you can make changes if you see one of these lines goes out of range or something else happens. Here is, for example, blue 1, which just gave it a name. And then here I have all my different process parameters. I can program this machine. I can even set exactly the height of my milling tool. And every time I'm running the same blue 1, I'm going to set it up exactly the same way. So there's really good for reproducing the same product all over again. Okay, and then I can program these cutoff values. Basically, let's say if I have a temperature threshold, and I don't want it to go over, let's say 80 C, I can say once it reaches that point, please let's reduce our speed or our energy input to bring the temperature back down. Or I can shut the machine off as well. That's another setup feature. I can do net power calibration. That allows me then basically just to show the energy input from the machine from the product itself without any machine input, because the machine, as it's running, it's already consuming energy. So by doing a net power calibration, I set all these values to an absolute 0 point, and then basically it's only showing me the energy that I'm using to disperse my product. That's also good for when I'm upscaling. This is just a quick slide on what the software looks like. Right now, that's the older Windows 7. We're going to come out with a whole new version, Windows 10. So that's going to be a totally different look. Okay, then finally, coming towards the end, we have a really nice applications lab at VMA in Germany. We have a lot of capabilities, vacuum dissolvers, with really good engineers, so we can run trials there and video conference you in, let you take part of these trials. But we also have the capability at our Wallingford lab, so that's only one side of the lab. There is more equipment on the other side. We just installed the latest AE6, the one I showed you before with that C control technology. We have CV3 up there. We have all the different milling attachments and dispersing tools, so if we want to do fine grinding. And I have a beautiful brand new horizontal SL mill. So these are the two new pieces of equipment that I have now in the lab that allow us to really do the entire range of all different products. Okay, so in Wallingford A-class laboratory, we basically can show you, the performance of the equipment, how it works with your product, sample the different accessories and, evaluate different milling tools. We can scale up, to larger equipment. Again, it's very important to recognize the advantage you have that having somebody from big right on hand to help us with formulation questions or improve the product overall. It also can be used as just a showroom to have customers, and we had a customer just this week who came in to review the technology and get familiar with it without running any product. And we can also use it as a seminar location. We have big conference rooms, so if customers say, hey, you know what, I have 10 technicians or, for my entire team, want to come down for a day, would you, make that available? Then we would do that at a very low cost, and we can make that possible. Okay, so that I think covers everything from my end. I will open up for questions, and thank you very much for the attention.
Yeah, great job, Andy. As always, definitely, some good information. So there's a quick poll, a survey I put up. There's just 4 quick questions, if you wouldn't mind selecting your answer there. But also, while you're doing that, if you have any questions for Andy on dispersion milling, the lab in Wallingford, or anything related, please just type them in the chat. I'll get notice of those and pass them along to Andy. Andy, while people are either entering questions or filling out their surveys, are there typical questions you get when someone's looking at this type of equipment, getting into or stepping up their technology around dispersion and milling?
Yeah, sure. I mean, we get a lot of questions about the design of our basket mill system, or even the horizontal mills and so on, and the technology. And they're really impressed with the ingenuity behind, also the modularity, of course, that we have the ability to really use a simple dissolver and upgrade it to be used with any type of milling attachment. So that's a really unique system, and gives customers a lot of confidence in the equipment, that they're not just buying one piece of equipment to use for one application, but it's very multifaceted in that way, to really, it's a very good equipment to be used for many different applications. And then obviously upscale, how easy does it upscale? And all of our equipment, except the APS system, I explained that the challenges there for upscaling, but the basket mill or even our horizontal mills are excellent, almost one-to-one upscale capability. We have data on that as well we can share with you. So if you're looking for production grade capability, we have some really, really good solutions there.
Yeah, and that's one thing. I've heard you do this presentation several times, and the thing that I keep coming back to is the modularity and the ability to upscale. If you start small and then you grow into a larger production machine, that's just an excellent use of the technology, the investment, as well as your space.
Yeah, and then there are so many unique applications that we see out there. I mean, we get more and more calls, about vacuum. People are interested. They say, "What's the benefit of using vacuum?" Mm-hmm. A vacuum system is good, especially when I'm also milling, because now the vacuum, the air bubbles, a lot of times tend to act like as little air mattresses, buffering the flow of the beads and increasing milling time and also efficiency. And if I can remove those, I have a more homogeneous product flow, and I'm able to put more energy into my mill base. And that should also improve my milling performance. So that's important. But secondly, I think also if you have a lot of foaming by using air, when you want to transfer from, especially manufacturing, you want to transfer the product from one container to another. Well, if I have a lot of foam, then that's going to take a lot of time. So by having the ability to take the foam out completely or remove it, now I'm much faster in transferring my product. So there is a lot of good things. We have also, like I didn't touch it, we've for our lab or even manufacturing scope for very viscous materials, we have a really nice wall scraper system that allows you to remove the product from the container wall and push it back into the middle for proper dispersion. So, a lot of different things that are available to improve the process.
That's excellent. That's excellent. Yeah, it looks like about half of the people have filled out their survey, so that's good. Get some information in. I know one of the questions was about having a webinar strictly on production dispersion. So looking forward to seeing what people have. If there's any time that you want a specific presentation, you can definitely contact us. Let me put Andy's email right in the chat here.
And also, if you saw in the presentation, if you have time or you're interested in the technology, go on dispermat.com. It's a great website. It gives you really a good overview over the different pieces of technology that we have, all the way up to manufacturing. It's a really nice site. It opens up the actual catalog pages for you. You can flip through them, and you can read through all the different model types, different sizes, power requirements. So we cover the attachments in detail, so you can see them up close. So it's a really good site to review if you're interested.
Yeah, I did just put that site URL address in the chat, as well as Andy's email. If you have any questions or think of anything after the fact, feel free to contact him directly. As I mentioned too, you'll receive an email with a link to this recording, including this chat and this discussion as well. So please take a look at that at a later time, share it with colleagues, customers, anyone who you think will benefit. And if at any time you're looking for a custom presentation or or information about a specific application, contact Andy. He'll definitely help you out. You know, he gives presentations and talks to folks all the time. So with that, I don't see any questions. If you have any questions, log them in the chat box here, and we just have a couple minutes left here. Also look for future invites to webinars like this. This is our second time out using this Click Meeting platform. It seems to be working a lot better than our old system, so we're happy about that. Definitely from our side of things, hopefully it's a little more intuitive from your side as well. So with that, I think we'll end it. Thank you for attending. We really appreciate your time. Hope you learned something. Don't hesitate to reach out to any of us. Andy, his email directly, or you can hit respond or reply to any of the emails you get regarding this webinar with the recording link. It'll come to marketing, and we'll get it to Andy and make sure he gets in touch with you. So appreciate it, Andy. Thank you, as always. Thank you for your expertise and knowledge. Thanks, everyone. Have a great afternoon.
Thanks, everybody. Enjoy the rest of your day and the weekend. Bye.